Okay, very simply, let's see what the temperature is for the really hot one. So Ava, what do you got?
81 degrees.
81 degrees Celsius, which is what, Zay?
81 degrees Celsius?
Yep.
Wait a minute. It's not on here.
Oh, it's off the chart?
Yeah.
What's 80?
There's no 80.
What's 79?
174.2 degrees.
100 and say it again?
174 degrees, 0.2 Fahrenheit.
Okay. Off the chart. Whoa. Emily, what's the room temperature reading?
27 degrees Celsius.
27 degrees Celsius is
80.6 degrees Fahrenheit.
80.6 degrees Fahrenheit. Okay, that's like roomy temperature. It's a little bit warm in here. Victoria, what's the cold one?
7 degrees Celsius.
7 degrees Celsius.
44.6 degrees Fahrenheit.
44.6 degrees Fahrenheit. So you guys can see our temperature range, right? Ladies, thank you very much. Have a seat. All right, Jay, can I have a seat? Thank you very much. All right, so now what we're going to do is try to simulate a convection current. Yesterday, we talked about convection currents in terms of what? In terms of a lava lamp, right?
Yeah.
How does a lava lamp do convection? Isabella? Okay, so you have a heat source at the bottom, and the heat source, the heat source is also a light source, but the heat source causes the blobs to do what?
They flow up and down.
Okay, why do they go up?
Because it's a convection.
Why do some of the blobs go up on the lava lamps? We got to dig a little bit deeper. What's happening on the molecular level that causes the blobs to go up? Sarah?
The heat causes the vibrations, which causes the molecules to expand, which causes them makes them less dense, which causes them to rise.
Excellent. Okay, so they're getting warmer. They're vibrating more, which makes them expand a little bit, which makes them rise because they're less dense. Everybody, computers should be shut right now. You should be getting ready to take some notes. Okay? There, now. Hustle. Okay, and then when they rise to the top, they eventually cool down just a little bit, and then they contract just a little bit. The molecules move a little less fast, and they sink. And they're getting pushed out of the way. That's right. Hello?
It better not be brave. It better not be brave.
In just a minute.
I said it better not be brave.
Okay, I want you to predict really quickly what will happen when I put the super hot red colored water in the bottom. Predict it on your notes. Go. Write it down. We can do this quietly, thank you. Are you ready?
Yes.
I said you have to go quickly.
Yes, very quickly.
Sorry. Braden's got to go, so we're going to go fast.
Oh, man.
All right, here we go. I'm going to put the warm on one side. Then I'm going to do something cold on the other side. Okay? If you want to come up and stand up here to observe, come on up. Don't bump any of the stuff, please. Step on this side. People here sitting can stay over here. Okay?
I can't see.
Then simultaneously, we will have, careful on that side, please. Ice cube with a few drops here, and we'll see what happens. So immediately you can notice that it looks like
the heat is rising and the cold is falling.
we are.
Oh, my. Oh, hi. That's a little
So what are we observing here, folks?
A lot.
The blue is falling and the red is rising.
Because
The
heat
blue
rises.
is falling and the red is rising, okay?
because of convection.
What else? Does the red look different than the blue?
Yeah.
Yes.
How so?
Because it feels like the red is like more around than the blue.
The blue looks more like,
It's just like
Swervy and
Swervy
hair.
and like
and that
silk.
looks like
It's like
actually
silk.
the water.
It's like hair.
okay.
Yeah.
Yeah, some people would call that like ribbons.
Yeah.
Okay. One thing that can be helpful is to set up a little backdrop of white so you can actually see what's going on. So you can see very clearly that the red is staying at the top and the blue is kind of all over the place in different ribbons. The fact that the red is like a cloud gives us another hint about how something acts when it's warm. It spreads out because it's moving faster. It's like a cloud. The blue sticks in these like little ribbons because it's sticking a little bit closer together. It's not spreading out as fast.
It might also be because you put the dye, like you didn't switch the dye around to where it would just become blue. Like
But
you
the
just,
red dye, I plopped it in. That's true. It was a different mechanism of putting it in the water. It's a good point.
Wait, I'm like seeing like less red.
And so what we're demonstrating here, folks, is convection currents. When we first put the red in and it starts to rise, and we first put the blue in and it starts to sink, that's the moment you have a convection current.
And now it's
this
like-
does not have a consistent heat source, so the convection current doesn't keep going. But it's demonstrated just for that quick moment.
It's like frozen now. It's